To study about mineralogy and minerals in general. To discuss the physical properties of minerals. To discuss the classification of minerals. Introduction. Different geological processes are responsible for the concentration of minerals in the parts of crust. Quartz contributes about 70% of the continental crust and is the most common mineral. Minerals which contain both silicon and oxygen are known as silicates. Oxygen and silicon can be joined together in different ways to form silicate structures like feldspar and augite, olivine, etc. Figure 1. About 96% of the minerals found in Earth's crust are silicates. There are over 100 elements known presently, but over 99% of the Earth's crust is composed of just 8 elements, i.e. oxygen, O, silicon, C, aluminium, Al, iron, Fe, calcium, Ca, magnesium, Mg, sodium, Na, and potassium, K. About 4,000 plus minerals have been so far discovered, out of which only a few hundred are considered to be common. An economic concentration or reserves of metallic minerals in a rock is known as ore. Non-economic minerals like quartz, feldspar and calcite which are found in association with ore minerals are known as gangue, pronounced gang, and are considered waste. It is insufficient to form an ore from average concentration of minerals in the crust. Figure 1. Minerals. Source. 16.1 Mineralogy. Mineralogy is the branch of science which deals with the physico-chemical study of naturally occurring solid and crystalline materials. We can also say that it is the scientific study of all aspects of minerals concerning with conditions of formation during their origin and natural distribution. Internal structure of crystal, physical properties and chemical composition of minerals all are included in mineralogy. A mineral is a homogeneous naturally occurring solid substance formed by inorganic processes having a definite but not fixed chemical composition with an ordered atomic arrangement. 16.2 Chemical composition of minerals. Elements are the building blocks of minerals. Geochemical factors such as element abundance, solid solution limits, mineral stability, place a limit on the composition and stability of naturally occurring compounds, hence, there are relatively less number of minerals. Minerals and synthetic compounds may have identical structures. However, they differ in the fact that minerals are rarely pure substances and typically show wide variation in their composition. According to the composition, variation of minerals ranges from pure elements Fe, O, Ag with relatively simple compounds e.g. PbS galena, K-sisulfite to very complex compounds e.g. steenstropine. Chemically simple minerals, CO2, do not necessarily have simple structures, e.g., alpha quartz. Chemical classifications of minerals are based on the predominant anion or anionic group. The following classes are recognized. 1. Native elements. 2. Sulfide, telluride, arsenide and selenide minerals including sulfosalts of antimony and bismuth. 3. Halides. 4. Oxides. 5. Hydroxides. 6. Carbonates. 7. Nitrates. 8. Borates. 9. Chromates. 10. Tungstates. 11. Molybdates. 12. Phosphates. 13. Arsenates. 14. Vanadates. 15. Silicates and aluminosilicates. Because of the dominance of oxygen, silicon and aluminum in the earth, silicates and aluminosilicates are quantitatively the most important class of minerals. Minerals of mixed anion composition, e.g. F in topaz or apatite, S in pyrite, O in talc and mica, Cl in biotite, are usually classified according to the nature of the dominant anion. Hybrid minerals, such as valerite and tochilinite, are sulfides containing layers of hydroxides, and are not common. Each major compositional class of minerals is subdivided into groups of minerals having similar crystal structures. Table 1. Table 1. Classification of minerals. Mineral group anionic. Or anionic complex. Representative minerals. Native elements sulfur, gold, silver, copper, diamond graphite sulfides S2 pyrite, galena, sphalerite, chalcopyrite oxides O2 hematite, magnetite, chromite halides Cl2, phyllite, fluorite sulfates SO4 2 anhydrite, gypsum, barite carbonates CO3 2 calcite, dolomite phosphates PO4 3 apatite. Silicates CO4 2 quart, feldspar. 16.3 Structural classification of silicates. The silicate and aluminosilicate class comprise orthosilicates, cerosilicates, inosilicates, phyllosilicates and tectosilicates, etc. Each of these divisions is further subdivided into mineral groups of different structure, e.g. the cyclosilicates into beryl, tourmaline and axonite groups. The divisions arise because atoms of similar size and bonding character adopt similar structures with a particular anion or anionic group. Hence, minerals of very different composition possess the same crystal structure. Silicates are compounds where C and O are abundant and are major mineral components of the Earth's crust and mantle. The basic unit for all silicates is the CO4 4 tetrahedron figure 2. Variety of silicate minerals are produced by the CO4 4 tetrahedral linking to self-similar units sharing 1, 2, 3, or all 4 corner oxygens of the tetrahedron. Silica minerals are classified based on how the silica tetrahedral are linked. O2. C4+ equals. Figure 2. Silicate structure, CO44. Tetrahedra may be isolated or be linked in rings, single chains, double chains, sheets, or frameworks. Let us discuss. 1. Nesosilicates, independent, isolated tetrahedral group, CO4 4. When the isolated tetrahedra are linked by the bonding of each oxygen ion of the tetrahedron to a cation, the cation in turn bond to the oxygen of other tetrahedral, figure 3a. Thus the tetrahedra are isolated from one another by cations on all sides. The ratio of oxygen to silica is 4, 1. Examples of such silicate minerals are olivine, garnet, zircon, etc. 2. Cerosilicates double tetrahedral group, C2O7, 6. In this type 2 tetrahedra are linked by a single oxygen atom, or in other words, 2 tetrahedra share 1 oxygen, figure 3b. The ratio of oxygen to silica is 2, 7 or 3.5, 1, figure 3b. Example of this type of silicate structure is epidote, melolite. 3. Cyclosilicates, ring structure, C6O18, 12 or C309, 6. When angular position of tetrahedra is such that it forms a ring. Closed rings of tetrahedral each sharing 2 oxygen, figure 3c. The ratio of oxygen to silica is 3:1. It forms following 3 types of closed rings. Each of 3 tetrahedra sharing an oxygen ion such as in mineral benitoite. Each of 4 tetrahedra sharing an oxygen ion such as in mineral axonite. Each of 6 tetrahedra sharing an oxygen ion such as in mineral beryl. A, B, C. Figure 3. Crystal structure of A. Nesosilicate, B. Cerosilicates, C. Cyclosilicate minerals. 4. Inosilicates. A. Single chain, CO3, 2. Single chains also form by sharing oxygen, but in this case, 2 oxygens of each tetrahedron bond to adjacent tetrahedra but in an open-ended chain instead of a closed ring. Single chains are linked to other chains by cations, figure 4a. The ratio of oxygen to silica is 3:1. Example of such silicates are the pyroxene group of minerals. B. Double chain, C4O11, 6. These are continuous double chains of tetrahedral alternatively sharing 2 and 3 oxygen. In this case, 2 single chains combine to form double chains linked to each other by shared oxygens. Adjacent double chains linked by cations form the structure of the amphibole group of minerals, figure 4b. A common mineral, hornblende has a complex composition including calcium, sodium, magnesium, iron and aluminium. The ratio of oxygen to silica is 2.75:1. A, B. Figure 4. Crystal structure of A. Single chain and B. Double chain silicate minerals. 5 phyllosilicates, sheet silicates, C2052. Sheets are structures in which each tetrahedron shares 3 of its oxygens with adjacent tetrahedra to build stacked sheets of tetrahedra. Cations may be interlayered with tetrahedra sheets, figure 5a. The ratio of oxygen to silica is 2.5:1. The micas and clay minerals are the most abundant sheet silicates. The minerals with sheet structures can be separated into extremely thin sheets. 6 tectosilicates, 3D framework, CO2, 0. 3-dimensional framework form when each tetrahedron shares all its oxygens with other tetrahedra, figure 5b. In this silicate structure, the ratio of oxygen to silica is 2:1. Minerals of feldspars and quartz are the examples of this type of silicate structure. A, B. Figure 5. Crystal structure of A. Phyllosilicate minerals and B. Tectosilicate minerals. 16.4 Physical properties of mineral. The mineral can often be identified in the field using basic following properties, figure 6. 1. Color. 2. Streak. 3. Hardness. 4. Cleavage or fracture. 5. Crystalline structure. 6. Diaphanity or amount of transparency. 7. Tenacity. 8. Magnetism. 9. Luster. 10. Odor. 11. Taste and 12. Specific gravity. Figure 6. Properties of minerals. One. Color. Idiochromatic minerals are said to be self-colored minerals because of their composition. The color of these minerals is caused by the presence of elements in the chemical composition of the mineral. E.g., Cu in azurite blue, Cu in malachite green, Mn in rhodonite and rhodochrosite pink. Physical properties of minerals: diaphanity, tenacity, magnetism, color, streak, hardness, cleavage or fracture, specific gravity, luster, taste, odor, crystalline structure. Allochromatic minerals are said to be other-colored, as impurities in traces are present in their composition or due to defects in their structure. In these minerals, the color is a variable and unpredictable property. E.g., blue in amazonite orthoclase, yellow in heliodor, spodumene, and the rose in rose quartz. Pseudochromatic minerals are false-colored, due to tricks in light diffraction. In these cases, color is variable but a unique property of the mineral. Examples are the colors produced by precious opal and the Schiller reflections of labradorite. Play of colors. One of the salient features of color mechanisms is the play of colors. Interference of light reflected from the surface or from within a mineral may cause the color of the mineral to change as the angle of incident light changes. This gives the mineral a beautiful iridescent quality and colors to the minerals, for example, bornite Cu5Fe4, hematite, Fe2O3, sphalerite, ZNS, opal, and some specimens of labradorite plagioclase. It is sometimes seen on tarnished sulfides like chalcopyrite or pyrite and occasionally on an oxide or a silicate mineral. It is caused by an optical effect called interference. When light strikes a shiny, transparent layer at an oblique angle, the light rays or split part of the light is reflected off the upper surface and part goes into the layer. Some of the light that enters the layer is reflected off the bottom surface and exists parallel to the other reflection. However, white light is composed of a number of colors, each of which travels at a different speed in the layer. So when the split light rays emerge from the layer, they have been retarded and their wave patterns are out of synchronization with the part of the light reflected off the top of the layer. 1 or 2 colors will be in phase and the rest out of phase. The in-phase color will be very bright and the out-of-phase colors will be very pale or absent. Thus, we may see a rich, glowing color coming from a colorless, transparent stone, but only in one special direction. Colors due to wavelength of light. Minerals are colored because certain wavelengths of light are absorbed, and the mineral color then results from the combination of those wavelengths which reach the eye if light is not absorbed. The mineral is colorless in reflected or refracted light and is black if all wave of light are absorbed. Pleochroism may be present in certain minerals if light travels along crystallographic axes. A mineral may display more than one color when rotated or viewed at different angles. Cordierite specimens often display a clear white and violet color when rotated, indicating a dichroism quality. Color due to impurities. Tiny amounts as little as 0.1% of an impurity in the molecular structure of a mineral can determine that mineral's color. The amount and type of impurities affects the color of the mineral. Minerals with an inherent color have essential elements in them which cause their color. The examples are azurite and malachite, which have their strong blue and green color due to their copper in their atomic structure. But there are many minerals which have slight additions of color-causing elements in some specimens that cause it to be a different color. For example, pure quartz, CO2, is colorless, whereas amethyst, a purple variety of quartz, has its purple color caused by traces of the element iron. The amount of iron present determines the intensity of the color. Trace amounts of titanium or manganese turn quartz pink. Color due to charge transfer. When two or more elements in a mineral exchange electrons, then this is called charge transfer. The movement of electrons results in selective absorption of light. For example, sapphire. Sapphires contain small amounts of titanium and iron. The electron transfer between T and Fe causes light in the yellow through red spectrum to be absorbed, producing the deep blue color sapphires. Aquamarine. Small amounts of iron in valence states Fe2+ and Fe3+ cause an electron transfer that absorbs red light, resulting in the color blue. Tourmaline. When manganese Mn2+ and titanium T4+ swap electrons, it creates a yellow-green color. 2. Streak. Streak is the color of the mineral in powdered form. The streak of a mineral is quite different than the mineral. Although the color of a mineral may vary, the streak is usually constant and is thus useful in mineral identification. Streak is a more accurate illustration of the mineral's color. Streak is a more reliable property of minerals than color for identification. 3. Hardness. Friedrich Maas in 1812 developed a standard scale for calculating the extent of hardness. Hardness varies greatly in minerals. Its determination is one of the most important tests used in identification of minerals. Hardness is the resistance offered by smooth surface of a mineral on scratching. The hardness of a mineral might be said to be its scratchability. Hardness, like many other physical properties, depends upon atomic structure of mineral. It varies with density of packing in structure. On the basis of their relative hardness, minerals are ranked from 1 to 10. Softer minerals are scratched by harder minerals. Mohs scale is based on the 10 index minerals while other minerals are ranked relative to these. For instance, a mineral having hardness of 6.5 can scratch feldspar but not quartz. Mohs hardness scale: talc soft gypsum, calcite, fluorite, apatite, feldspar, quartz, topaz, corundum, diamond hardest. 4. Cleavage. In most of the crystals, strength of bonding in all directions is not equal, which will be liable to crack along crystallographic directions, representing a fracture property by reflecting the fundamental structure, which can be analytical. Regular flat faces which resemble growth faces like in calcite and mica are the results of perfect cleavage. Cleavage is the property of a mineral to break along planes where bond strength is low in the chemical bond. A cleavage is said to be imperfect or parting when it is less developed. Parallel sheets are produced when some minerals break along one dominant plane of cleavage, while prism or blocks results from breakage along two or more planes. Table 2. Table 2. Types of cleavage. Cleavage type angles. Example. Basal cleaves in one direction, mica's cubic cleaves in three directions at 90° to one another. Rock salt, halite, galena, etc. Rhombohedral cleaves in three directions parallel to the faces of the rhombohedron but not at 90° to one another. Calcite. Octahedral cleaves in four directions parallel to the faces of the octahedron. Diamond and fluorite. Dodecahedral cleaves in six directions parallel to the faces of the dodecahedron. Sphalerite. Prismatic cleaves in two directions parallel to the prismatic faces. Pyroxenes and amphiboles. Pyramidal cleaves in four directions parallel to the pyramidal faces. Scheelite. Fracture. Fracture describes the quality of the cleavage surface. Most minerals display either uneven or grainy fracture, conchoidal curved, shell-like lines fracture, or hackly, rough, jagged fracture. If the mineral contains no planes of weakness, it will break along random directions called fracture. Following kinds of fracture patterns are observed. Conchoidal fracture breaks along smooth curved surfaces. Fibrous and splintery, similar to the way wood breaks. Hackly, jagged fractures with sharp edges. Uneven or irregular, rough, irregular surfaces. Parting. Parting is also a plane of weakness in the crystal structure, but it is along planes that are weakened by some applied force. It therefore may not be apparent in all specimens of the same mineral, but may appear if the mineral has been subjected to the right stress conditions. 5. Crystal form. Crystal form is the external expression of the internal ordered arrangement of atoms. During mineral formation, individual crystals develop well-formed crystal faces that are specific to that mineral. They reflect the internal symmetry of the crystal structure that makes the mineral unique. Crystal faces commonly seen on quartz are growth faces and represent the slowest growing directions in the structure. Quartz grows rapidly along its C-axis, threefold or trigonal symmetry axis, direction, and so never shows faces perpendicular to this direction. On the other hand, calcite rhomb faces and mica plates are cleavages and represent the weakest chemical bonds in the structure. The crystal faces for a particular mineral are characterized by a symmetrical relationship to one another that is manifest in the physical shape of the mineral's crystalline form. Crystal forms are commonly classified using 6 different crystal systems, figure 7AF, under which all minerals are grouped. The 6 major crystal forms are given below. A cubic or isometric. The simple cubic system has one lattice point on each corner of the cube with each lattice point shared equally between 8 adjacent cubes. E.g. halite is rock salt. A, B, C. D, E, F. Figure 7, a cubic. B, tetragonal. C, orthorhombic. D, hexagonal. E, monoclinic. F, triclinic. Source. B, tetragonal crystal lattices result from stretching a cubic lattice along one lattice vectors, making the cube a rectangular prism with a square base. E.g. zircon. C, orthorhombic lattices are made by stretching a cubic lattice along 2 lattice vectors by 2 factors, forming a rectangular prism with a rectangular base. All 3 bases intersect at 90-degree angles and the 3 lattice vectors are mutually orthogonal. E.g. aragonite. D, hexagonal lattice has the same symmetry as a right prism with a hexagonal base. Graphite is an example of a hexagonal crystal. Monoclinic lattice is described by vectors of unequal length that form a rectangular prism with a parallelogram as base. Two pairs of vectors are perpendicular, while the third pair makes an angle other than 90 degrees. E.g., orthoclase. Triclinic crystal is described by vectors of unequal length. All three vectors are not mutually orthogonal. E.g., copper sulfate. 6. Tenacity. Tenacity is the tendency of a mineral to deform plastically under stress. Minerals may be brittle and can be fractured under stress, such as silicates and oxides. Minerals can be sectile, as they can be cut with a knife, or they can be ductile by deforming readily under stress, as does gold. The following chart below gives the list of terms used to describe tenacity and a description of each. Table 3. Table 3. Various terms related to tenacity. Term description. Example. Sectile mineral can be cut with a knife, resulting sheath breaks up under a hammer. Graphite, steatite, gypsum. Malleable. A slice cut from mineral can be hammered out into thin flat sheets. Native gold, silver, copper. Flexible. When applied pressure, a mineral can bend but does not return to its original position when the pressure is removed. Elastic. The mineral or thin plates of laminac from it can bend and returns to its original position after the pressure is removed. Micas. Brittle. The mineral crumble or shatters easily. Iron, pyrite, apatite. Fluorite. Ductile. The mineral can be drawn into wires. Copper. 7. Luster or transparency. Luster refers to the general appearance of a mineral surface in reflected light. Mineral luster can be metallic or non-metallic. The mineral is metallic when it is opaque and reflects like metals. Minerals with metallic luster are usually opaque and have a colored streak. Non-metallic luster can be 1. Vitreous, e.g., quartz, calcite. 2. Resinous, e.g., sulfur. 3. Pearly, e.g., barite. 4. Greasy, e.g., calcite. 5. Silky, e.g., asbestos. 6. Adamant, e.g., feldspar. Alternatively, it is non-metallic when mineral does not reflect light. When the mineral looks like paraffin or wax, then it is said to be waxy. Examples include jade and chalcedony. The mineral is vitreous when it looks like broken glass, and it is pearly when it appears iridescent, for example muscovite and stilbite. The mineral looks fibrous like silk, then it is termed as silky. Examples of silky minerals include asbestos, ulexite, and the satin spar variety of gypsum. The mineral is greasy when looks like oil on water. Resinous minerals looks like hardened tree sap, resin, example is amber. Adamantine looks brilliant, like diamond. Greasy minerals resemble fat or grease. A greasy luster often occurs in minerals containing a great abundance of microscopic inclusions, for example opal and cordierite. 8. Specific gravity. Specific gravity is a definite physical property calculated in gram per cc. It can be calculated by the measurement of volume with displacement of water in a graduated cylinder and the mass. Specific gravity is a dimensionless quantity. Different minerals have different specific gravity, e.g., iron 8, lead 13, and gold 19. The range of specific gravity is from 2.6-3.5 for silicates and from 5 to 6 for sulfides. Mineral with various specific gravity are summarized in Table 4. Specific gravity, Sg, is calculated by the determination of the weight in air, Wa, and the weight in water, Ww, and specific gravity can be calculated using following formula. Sg equals Wa Ww. Table 4. Mineral with various specific gravity. Mineral composition. Specific gravity. Graphite C2.23 quartz CO2 2.65 feldspars K, Na Lc30H 2.62.75 fluorite CaF2 3.18 to. Environmental sciences. Environmental geology. Mineralogy. Minerals, types. 16.5 Geological processes of minerals formation. 1. Magmatic deposits. Magmatic deposits result from simple crystallization and concentration by differentiation of intrusive igneous masses. They have high melting points so that they can coexist and get crystallized from silicate melts at temperatures above 800 C. Granites, granodiorites, and rhyolites, along with rich minerals like quartz, muscovite, and alkali feldspars are felsic igneous rocks. These minerals are usually light in color, and the color is not always diagnostic. Pegmatite Peg is a third mineral environment showing concluding stages of fractionation in igneous rocks. It is very coarse-grained and similar to silicic igneous rock in composition with high silica. There are certain elements which readily do not substitute in abundant minerals and are termed as incompatible elements. In pegmatites, they made their own minerals by accumulation. Minerals containing the incompatible elements, Li, B, B, P, Rb senior, Y, Nb, rare earths, Cs, and Ta are typical and characteristic of pegmatites. Deer et al. 1962, 1974, 1980. Rocks composed mostly of pyroxene, calcium-rich plagioclase, and minor amounts of olivine make up the mafic family of igneous rocks. The mafic magmas are somewhat more viscous than the ultramafic magmas, but they are still fairly fluid. The low silica and gas contents make ultramafic very fluid, i.e., they have a low viscosity, or resistance to flow. Ultramafic rocks are given names depending on whether they are intrusive or extrusive. Peridotite is the name given to intrusive ultramafic rocks, whereas komatiite is the name given to extrusive ultramafic rocks. Peridotite and komatiite are recompositionally identical. Their textures, however, are different, reflecting their mode of formation. Peridotite appears to be the dominant rock type of the upper mantle. 2. Sedimentary mineral deposits. The formation of sedimentary rocks is accompanied by three processes. The first process is the weathering, which produces the materials that a sedimentary rock is composed of by mechanical freezing, thawing, and chemical dissolution of minerals, formation of new minerals, clays, interaction between atmosphere, hydrosphere, and Earth's surface rocks. The second process is the transport, which moves these materials to their final destination. Environmental sciences. Environmental geology. Mineralogy. Minerals, types. Rivers are the main transporting agent of material to the oceans. Glaciers are at times important. During transport, the sediment particles will be sorted according to size and density, gold placers, and will be rounded by abrasion. Material that has been dissolved during weathering will be carried away in solution. Winds may also play a role. Sahara, East, Central Atlantic. The sorting during transport is important because it is the reason that we have distinct clastic rock types, conglomerates, sandstones, shales. The third process is the deposition of sediment, which occurs at a site with a specific combination of physical, chemical, and biological conditions, i.e. the sedimentary environment. 3. Metamorphic rock mineral. Metamorphic processes occur to make adjustments between the chemical potential of any system and the changes in temperature and pressure. Metamorphism involves both chemical and mechanical changes but in varying proportions. Metamorphic minerals and rocks provide many valuable resources, marble and slate the two most widely used. Metamorphic rocks are formed when the precursor materials, igneous, sediment, etc., are buried deeply and are consequently brought into an environment of high pressure and temperature. Therefore, they are most commonly encountered in the core zones of mountain belts, uplifted root zone, in old continental shields, and as the basement rock below the sediment veneer of stable continental platforms. Metamorphic rocks and associated igneous intrusions, from rock buried so deep that it melted, make up about 85% of the continental crust. Metamorphic rocks may contain relic structures, such as stratification, bedding, and even such features as sedimentary structures or volcanic textures. 4. Hydrothermal mineral deposits. Hydrothermal mineral deposit is the fourth major mineral environments. The elements it contains and the minerals formed by this process are very different from regional and contact metamorphic rocks, therefore, it becomes inevitable to consider them as isolated group. With increase in depth, there is a scarcity of water, so minerals in the form of magma. Environmental sciences. Environmental geology. Minerals, types. Approach to the Earth's surface through crust. Woods Hole Oceanographic Institute, USA, explored the floor of ocean with the use of submersible craft and discovered the hot water's plumes which were coming out along the oceanic ridge. The plumes of hot water contain manganese, copper, iron and zinc, which are dissolved sulfide metals, and the mineral deposits produced by them were termed massive sulfides. When viewed in the lights of submersible craft, the water coming from tall hydrothermal vent resembled the smoke coming from chimney due to precipitated minerals, and the vents were named as black smokers. These may be subclassified as high-temperature hydrothermal (HTH), low-temperature hydrothermal (LTH), and oxidized hydrothermal (OXH). Sulfide minerals generally consist of minerals which are present centrally and on the right-hand side in the periodic table, e.g. Cu, Ag, As, SbSn, Pb, Zn, Hg, Cd, and are generally known as chalcophile elements. Sulfides are mostly hydrothermal, but they may occur in metamorphic and igneous rocks. Silver, tungstate minerals, the tellurides chalcopyrite, gold, bornite, and molybdenite are all high-temperature hydrothermal minerals, and the hydrothermal minerals with low temperature include pyrite, barite, cinnabar, gold, and cassiterite. Sulfide minerals will weather by oxidation to form oxides of the sulfates and carbonates of the chalcophile metals, as they are not stable in atmospheric oxygen. These types of mineral are the feature of oxidized hydrothermal deposits and are known as gaussins. They show characterized mark, i.e. red yellow stains of iron oxide on the surface of rock. They generally separate mineralized zones at depth and are very common in Colorado. 16.6 Mineral classification. Minerals can be arranged and classified, figure 8, on the basis of their chemical composition and internal crystal structure. Based on chemical classification, there are 7 major mineral groups which are given below. 1. Silicates. 2. Native elements. 3. Halides. 4. Carbonates. Environmental sciences. Environmental geology. Minerals, types. 5. Oxides. 6. Sulfates. 7. Sulfides. Silicates. Silicates are the most abundant minerals in Earth's crust and are composed of oxygen and silicon elements in combinations with the cations of other elements. Silicate minerals are most important rock-forming minerals and are regarded as building blocks of the common rock-forming minerals. According to an estimate, about 27% of all known minerals and about 40% of common rock-forming minerals are silicates. Silicate minerals make up approximately 90% of rocks in the Earth's crust. The common rock-forming silicates minerals are listed here. Olivine. Garnet. Pyroxenes. Amphiboles. Micas. Feldspars. Feldspathoids and silica group. Among all the minerals, plagioclase feldspar is the most abundant minerals in the Earth. Native elements. Native elements are the minerals which consist of a single element. Examples are gold, O, silver, Ag, copper, Cu, iron, Fe, diamonds, C, graphite, C, and platinum. Point. Environmental sciences. Environmental geology. Minerals, types. Halides. Halides consist of halogen elements, chlorine Cl, bromine, bridge fluorine F, and iodine I, forming strong ionic bonds with alkali and alkali earth elements such as sodium, Na, calcium, Ca, and potassium K. Examples include halite, Nacl, and fluorite, CaF2. Carbonates. Carbonates are anionic groups of carbon and oxygen. Carbonate minerals result from bonds between these complexes and alkali earth and some transitional metals. Common carbonate minerals include calcite CaCO3, calcium carbonate, and dolomite Camg, CO3-2, calcium, magnesium carbonate. Oxides. Oxides are minerals that include one or more metal cations bonded to oxygen or hydroxyl anions. Examples are hematite, Fe2O3, magnetite, Fe3O4, corundum, Al2O3, and ice, H2O. Sulfates. Sulfates are minerals that include SO4 anionic groups combined with alkali earth and metal cations. Anhydrous, no water, and hydrous water are the two major groups of sulfates. Barite BaSO4 is an example of an anhydrous sulfate, and gypsum CaSO4 2H2O is an example of a sulfate. Sulfides. Sulfides are minerals composed of one or more metal cations combined with sulfur. Many sulfides are economically important ores. Pyrite Fes2 or fool's gold, galena PbS, cinnabar HGS, and molybdenite Mos2 are a few commonly occurring sulfide mineral. Environmental sciences. Environmental geology. Mineralogy. Minerals, types. Figure 8, classification of mineral. Halides. Carbonates. Oxides. Sulfides. Silicates. Classification of minerals. Native elements. Sulfates. Olivine, pyroxene, hornblende, biotite, muscovite, feldspar, quartz. Gold, silver, copper, iron, diamonds, graphite, platinum. Halite, fluorite. Calcite, calcium carbonate, dolomite, calcium, magnesium carbonate. Hematite, magnetite, corundum, ice. Barite, gypsum. Pyrite, galena, cinnabar, molybdenite. Mineral group examples. Environmental sciences. Environmental geology. Mineralogy. Minerals, types. 16.7 Uses of minerals. Industrial uses. Calcite is mined primarily to make cement, be used as a flux in the smelting of metallic ores, be used as a fertilizer, or used as a building stone or construction material. Limestone is used as crushed stone in road construction and other construction, for ballast in railcars, for the manufacture of cement, as a filter, to absorb CO2 emissions at coal plants, to adjust pH in soil, and in animal feeds. Garnet is ground to a variety of sizes to be used as an abrasive. Garnet is also used in sandpaper, sanding belts, discs, and strips. Gypsum is used in wallboard and plaster products. It is also used to make Portland cement and has some agricultural applications. A small amount of very pure gypsum is used in glass making. Hematite is a common ore of iron because it contains about 70% iron. Once mined, the iron from the hematite is then mixed with other elements in order to make it into steel, the most common use of iron ore. Abrasives. Quartz sand is hard enough for woodworking. Corundum is the workhorse abrasive of sandpaper. Extremely hard, Moss 9, and sharp, corundum is also usefully brittle, breaking into sharp fragments that keep on cutting. It's great for wood, metal, paint and plastic. All sanding products today use artificial corundum aluminum oxide. Diamond paste is available in many grades for sharpening hand tools, and you can even buy nail files impregnated with diamond grit for the ultimate grooming aid. Diamond is. Environmental sciences. Environmental geology. Mineralogy. Minerals, types. Best suited for cutting and grinding tools, however, and the drilling industry uses lots of diamond for drill bits. Ceramic. The important geological sources for silica suitable for the ceramic industry are the pegmatites with well-developed crystals of quartz, vein quartz, and sandstones of high siliceous nature, high silica sands and orthoquartzites. Feldspars are used as fluxing material in the preparation of ceramic bodies, enamels and glazes. Commonly potash feldspars, orthoclase and microcline, are used for this purpose and soda feldspar is chiefly used for glazing purposes. Electrical. Coltan is a metallic ore composed of niobium and tantalum. Coltan is refined into metallic tantalum, which with its unique capacitor properties is then used in computers, cell phones, video game consoles, GPS, video cameras, and other microelectrical circuits. Gold has many practical uses in electronics. Its high malleability, ductility, resistance to corrosion and most other chemical reactions, and conductivity of electricity led to many uses of gold, including electric wiring. Summary. We studied about the composition, internal structure and properties of minerals. We studied about the mineral deposits found in the environment including igneous, metamorphic and sedimentary mineral deposits. We studied the classification and uses of minerals. Environmental sciences.